So updated the lecture note and posted in my e-learning. You can take a look at it. Yeah, even with previous section, there were lots of revision. So now it looks much better. So last time we talked about tree-level amplitude, and from today, so we will talk about torus amplitude. So last time, so we just considered. So let me sphere with lots of puncture, and that can be written. Sphere is four puncture we focus on. So this is called Shapiro amplitude. That will involve only the to fix the control gauge. There are 6, so therefore we just put the CC bar B, CC bar B, and then the rest is some dependence on the coordinate, and then you can fix 0, 1, infinity, and Z4 are the integrated out. Yeah, and then what we have done is essentially is equal to some constant times delta sum of ki, and then we have the d squared 4, Z4, and then you have the amplitude coming from vertex operator. And then you have ghost coming from ghost. So that's the, sorry, not times. And this is coming from vertex operator, product of B, and this product of C. And then if you carry out this integration, this integration will give you some something like a hypergeometric function. And this function has a pole at the S channel in the SDU, all channel in the minus alpha prime over S of 4 plus 1 is indeed. So this has a pole at. And this one will give you some string spectrum, bosonic string, bosonic string spectrum, including tachyon, and then massless mode and the high excitation mode. Yes. Thank you very much. Yeah, please point me out. It's recorded and all. So I told you lots of wrong information so far, and I have to make a comment on the video if I make a mistake. Okay, so today, we talk about one loop. It's more like this one. Torus amplitude. This one Phaton graph of the it's just you understand the one loop graph like this way. So we will consider the amplitude on this so this encodes, so therefore the quantum correction and so on, quantum correction. And so on. Okay, so again, so how many dimension of conformal Killing group. What is the dimension of conformal Killing group of torus? 2. 2 conformal Killing vector, and the what is the modular space or Riemann surface? What's the dimension? 2. Okay. Metric moduli or moduli. Okay. 2-dimensional moduli. So now new ingredient comes in. So last time, so in the for sphere we don't include metric moduli, but now we have metric moduli. So we have to carry out the integration over the metric moduli. And then first let's fix the conformal Killing vector. So again we need to introduce zero mode, CC bar 0. So we need to introduce zero mode of the C ghost. And indeed, in torus it's just as, and we start with the the torus with periodicity tau and 1 tau, where the metric is the flat. We start with this condition. And then, so in torus, it's a flat metric, so therefore it's easy to get the zero mode by just integrate over. Integrate over. So, as you learn Fourier analysis, here if you just have e to the e to the w. So w is equal to e to the sigma plus I tau. So it's more like a cylindrical coordinate. And if you perform the integral, it's only integral over a 2-dimensional flat mode. The high, so if you just expand CW as the constant mode, and you just do the Fourier expansion, so CW, W plus, and so on. And then, oh sorry, it also depends on W bar. I have to be careful. C depends on W psi. Yeah, C depends on W. Only holomorphic coordinate. Yeah. And then, so therefore, you can just to pick up the coordinate, you have to integrate over only over the all torus and pick up only this one. That's what you learn in Fourier analysis. So therefore, the zero mode of the ghost can be easily carried out, pick up by just integrating out on torus. This is situation on torus. And moreover, we need to, so here, as I mentioned, so in general amplitude, you have to carry out the metric, the integral over modular space of Riemann surface. So this is called fundamental domain. I call it F. And we have to perform the integral over here because of the, as I mentioned, so after fixing gauge, there is some physically inequivalent configuration. This is metric HAV space. Physically inequivalent configuration in the path integral. So you have this physically inequivalent configuration corresponds to this fundamental domain. So you have to carry that. And then by inserting this piece, HAB, HWW, and WW. Okay. Inserting this piece. Inserting this piece. That's what we have learned last time. Bar, HWW, bar. Okay, so we need to insert this piece. Insert and perform this integration. So to obtain this, how to say? It's a tangent. So as I mentioned, this is tangent vector of the dihumeral space. Tangent vector of dihumeral space. And we want to obtain the explicit expression of this piece. Okay, first. So to obtain this expression, first let's consider we just perturb this flat metric a little bit. So we just perturb delta HWW is equal to epsilon delta. So we just have some infinitesimal deformation of the metric like this way, so that the metric can be written as follows: dW plus epsilon W bar, dW bar plus epsilon bar W. Okay, so then yes. So if you perturb from here to here, okay. So then, as you can easily see, so once you write W is sigma plus I sigma 2, or maybe as before. Oh, sorry. I mean, I did it wrong. So here this is not correct. So W is indeed sigma plus I tau. Sorry. So this is the correct. So cylindrical coordinate is this coordinate, and once you map to the flat space, so we just W goes to Z, which is e to the minus IW. That's what we did. And W is more like the coordinate of cylinder, and we just identified left circle and right circle to get the torus. That's what we have done. So W is indeed sigma I tau. I don't want to use tau. Let's go T. Or maybe it's better to call it sigma 1 plus I sigma 2. Okay. So then let's look at the period. So therefore, new coordinate look like as follows. So new coordinate here, so new isothermal coordinate, so W tilde. If you write down W tilde is equal to W plus epsilon W bar, and this can be written W tilde plus W tilde bar. Okay, that's become flat metric. And now, so if you change the metric like this way, let's look at how the period will change. Period is this one on top. Okay. So then, so let's look at the period. So W plus epsilon W bar is sigma 1 plus I sigma 2. Okay. And plus epsilon W1, sigma 1 plus minus I sigma 2. So therefore, so it becomes 1 plus epsilon sigma 1 plus, it becomes 1 minus epsilon. I think I made some mistake. Yeah. Here, torus coordinate. Oh, I think P of this 6.1. Yeah, I think I made a mistake. No, so sorry. We need to identify to get this coordinate, as I mentioned last time. So this is d sigma 1 plus tau sigma 2 and square. So therefore, indeed, so to get the coordinate, you have to identify like this way. Sorry. So you have to use this coordinate. When tau is equal to I, you have just a rectangular one, rectangular torus. But if you can also tilt this tilt information and call this tau. Therefore, I have to include this tau here. Actually, sorry, tau bar. Okay, so then now everything's okay, and then here, so what you have is epsilon tau bar and sigma 2. Okay, now it's everything okay. So now, so here new coordinate W tilde has a periodicity. You just have periodicity which is epsilon epsilon 2 pi 1 plus epsilon and 2 pi 1 tau plus epsilon tau bar. Okay. That's the periodicity that show up here. It used to be you just identify tau plus sigma 2 and periodicity really come from here, show up here. Therefore, you just read off. So therefore, if you just consider the new complex structure tau tilde, it takes the following form. So you just take the ratio between them. And therefore, from here, if you take the epsilon is very small, then what you have, you just take the leading mode, and you get this. So therefore, the derivative of the I think again I made a mistake. You should tell me. Okay, this is opposite. Okay, so as you can see, yeah, W is proportional epsilon bar, and W bar is proportional epsilon. So therefore, so you just have a minus epsilon divided by minus 2I epsilon tau 2, and this one will get, you will get I times 2 tau 2. Okay, so this is the expression for tangent vector. So now we just want to insert this metric, the pairing between how to say, this is tangent vector and the cotangent vector in holomorphic part, and this is anti-holomorphic part. That's what we. So therefore, we just have carry out B tau H is equal to B squared W 4 pi squared H BWW. So this is this expression I have written down last time. H WW bar. And then you can just plug in and just so this is tau 2, sorry, tau 2. So do you understand why 4 by tau 2 will show up? So let's see, d squared pi 4 pi tau, and then 4 pi. Let's see, 4 pi. Squared H BWW, and you just plug in here. Okay, and this is indeed equal to 2 pi I. So again, so integrate over the torus is indeed just you get the zero mode. So you have BWW. It's tau 2. To get tau 2, you have, I just do the normalization. So this is 1 and tau 2, okay? Tau. So therefore, the area of this torus is indeed tau 2. Okay? In tau 2, that tau 2 cancel with this one. And with, I have 2 pi normalization in both. You have 2 pi square will cancel with 4 pi times 2, and you get 2 pi. Okay, so more precisely speaking, so that I should mention 2 pi square in that case. Yeah, I think this is the correct normalization in that case. Yeah. Sorry, thank you very much. There's a typo in my lecture. Okay, so that's what you get, and you need to insert this guy into the path integral. So at the end of the day, so what we get is n torus with n puncture the amplitude is G string N, and then 1/2 D squared tau, and then you just have a bunch of insertion. C bar, and everything 0. And then B1 0 is fixed. So one of the vertex operator is fixed. So one of the vertex operator fixed is C bar B0. C bar B0 means you have to keep vertex operator at the corner, and then the other operator can be integrated out. And then the other operator, which is I runs for 2 to n, and then you just have the usual form of vertex operator. And this integration is really carried out, this modular space of Riemann surface, fundamental domain. So that's what we need to carry out. So then this expression indeed, so dimension, so you can just insert, and the more precisely this is called H bar. So more precisely, you can just obtain 0 mode by carrying out the integral. So therefore, we can just write down this 0 mode, just constant mode, just by writing the integration form. So that this expression can be written G string n 1/2 D squared tau and tau 2. And then, so we already knew that integrate. So pairing between B and the tangent vector of the metric is give you just 0 mode here. So therefore, we can just indeed write down B0 bar C bar 0, and then you have a product of n. Now I rounds for 1 to here, so you get the just 0 mode Bj W bar. So now just carrying out squared H. So now carrying out the torus integral, you can get the just 0 mode of the torus. And this is indeed factorization occurs. So this is BC ghost, and this is X. Okay. So and then from now, so we will just evaluate each piece of correlation function. Any questions so far?
I don't quite understand how this tau 2 comes into
Here?
No, this tau 2.
Okay. Let me do the computation in that case. Yeah, you can ask. Let's see. 1 over 1 plus epsilon is what? It's equal to 1 minus epsilon plus epsilon square and so on. And dot. So therefore, this one is equal to indeed tau plus epsilon tau bar times 1 minus epsilon. If you just look at the leading order of epsilon, then this is equal to, if you order epsilon is just a tau plus epsilon tau bar minus tau. Okay. And then order epsilon square, and this is equal to tau 2 minus 2i epsilon 1, and that will give you that one. Any other question? Okay, so let's evaluate this piece when there's no puncture. So now we just look at the Transpartition function without any puncture. So let's evaluate no puncture case. So which is equal to 1/2 fundamental domain T squared tau tau 2 B bar C bar 0, and this is BC equals correlation function and X. That's what we're going to. And then so this one X is just a dx e to the minus s sigma and on torus. Okay. And this path integral can be written as trace. This is the Lagrangian formulation. For Hamilton formulation, this is e to the let's say p tau 2 plus h tau 1, and the appropriate normalization. It should be appropriate normalization. Tau. Oh, what are you doing? Am I correct? Sorry. So you have. Seems like a typo in lecture note. Oh yeah. Sorry. Tau 1 is this direction, right? Oh, okay. So sorry, it's correct. Tau 1 is here, and tau 2 is here, and times r. Times 2 pi I. So as you can see, so torus tau is just this direction is tau 2, and this direction is tau 1. So you just and then here. This is sigma 2 is indeed time direction, and this is spatial direction. So therefore, so time translation e to the 2 pi I times Hamiltonian times tau 2. Tau 2 is the length of time, and this I come from the Euclidean, just from Minkowski to Euclidean. And P is a spatial translation. And then spatial translation by tau 1 is just e 2 pi I times p times tau 1. This is you get this spatial slice to this spatial slice, and then you identify, okay? And then you just sum over all Hilbert space. That's the Hamilton formulation of this path integral. Do you understand? So given a Hilbert space on some spatial circle, and you just identify top and bottom by Hilbert space and Hilbert space. That is equivalent to carry out the path integral over the torus. So and this can be written. So we remember that the L0 minus L0 is equal to proportional to momentum. As far as I remember. Yeah, L0 bar, sorry. And the L0 plus L0 bar is proportional to Hamiltonian. Plus the Casimir energy. So this is the, remember the relation between the zero mode of Petersson generator and momentum and Hamiltonian. So from this relation, this can be written as trace of Q to the L0 minus C over 24, Q bar, L0 bar minus C bar over 24. So that's the partition function we will evaluate. And the trace is taken over all Hilbert space. Trace taken over all Hilbert space, and then we will carry out all this trace. So remember that the Hilbert space is just a start with the Hilbert space is just box space that is bound by 0k. This is the vacuum state, and you just apply all the alpha n1, alpha n2, and then k times anyway, alpha minus. What I'm doing here? What's the? Oh yeah. So my notation is different. Sorry. 1, 2, and 1 and 2, and so on. Alpha. So you just apply creation operator. Creation operator on vacuum, just bound by this Fock space. It's the same as harmonic oscillator. So then, I omit the mu. Essentially, all the generator has a mu indices for target space, n. But I omit the mu here now. So for timing, let's forget about the mu direction. Just fix some mu. Okay, and I call it this one is equal to this one is equal to n1 and 2. This is usual Fock space notation, nk. And trace of Hilbert space over q to the L0 minus c over 24. So this is a homomorphic part. I just look at. It's just a sum over all n and 1. K and 1 and 2 q to the L0 minus c over 24 and 1 and 2. Okay. So from here, so what are the dimensions? What's C? The number C. Once you fix the dimension, what's C in bosonic string? Central charge. Central charge of this one. Central charge is equal to bosonic string. Central charge is most important. Number of dimensions. So we fix the dimension, which means fix means we only look at the particular dimension. Dimension is 1. Wow, good. Central charge is equal to 1. So therefore, you have q to the minus 1 over 24. Okay. 1 over 24, and you have, so remember that the L0, alpha minus n, what is the commutation relation? What is the commutation relation between them? Do you remember? Oh, come on, this is the it should be proportional to minus n, and then what is the number here? N. Good. Good. So therefore, you just take. So just remember. So this one is just a. For instance, for vacuum is L0 equal to just 0, and then oh sorry, it's not 0. So L0 is just a q to the what is the momentum, right? Alpha prime over 4k squared. So remember, L0 is equal to alpha prime over 4k squared plus sum over alpha minus n. Okay, n runs for greater than 0. Okay, so this is the expression. So vacuum state only look at see this k squared part, and that will give you this one. Or maybe I should write down p squared. So, and then, so you just have a bunch of Fock space. So you have alpha minus 1. So the first excited state is this one. The second excited state is alpha minus square and minus 2, 0k. So you have a 2 state. Okay? And then third is alpha minus 1 cube, alpha minus 2, alpha minus 1, and then alpha minus 3. Okay? What else people can have? Is that all? I think that's all. So first we need to count how the alpha minus 1 acts on. So this contribution can be counted by 1 minus q. Can you see that? Do you understand? The contribution of alpha minus 1 coming from alpha minus 1 to the some power will give you 1 over 1 minus q contribution. Do you see that? Hopefully you see that. 1 minus q is equal to 1 plus q square plus q cubed and so on. Geometric series. Take. And vacuum corresponds to 1, alpha minus 1 corresponds to this guy, alpha minus 1 to the square corresponds to this guy, and so on. The next, we need to take a look at the alpha minus 2 contribution. And that will give you 1 minus q square, and so on, and so on. So therefore, at the end of the day, you get alpha. So that's the contribution from just trace over all the Hilbert space. Okay. Do you understand? Okay. For instance, this state corresponds to what? This state corresponds to how to create this state out of this power series. Q times q square. Okay. Q times q square. So here multiplication will automatically pick up this guy by just multiply this q and q square. Do you understand? This is very important, so I hope. And magically, so without knowing any mathematics, by just taking this generating series of this Hilbert space, we will get q to the alpha prime over 4, 1 over 8 tau. So this is called a Dedekind eta function. And you just sum over all dimension. So then what you get is you have to integrate over all the 0 mode over 2 pi d. So, and then we need to pick up, you just include both homomorphic and then anti-homomorphic part. You get that this part will give, oh, I missed q square. I think I should call k square instead of p square, whichever is okay, but anyway. Oh gosh, yeah. So then you have Dedekind eta function. Is that okay? So this is, I fixed dimension mu fixed. So then each dimension will give you 1 over eta. So if you consider homomorphic, anti-homomorphic, you get 2D. Okay, so then. Any question? Okay, so then now we need to evaluate BB bar, CC bar, 0. So now here we just consider the same thing. So you have include the, let's see, which one is correct? Order of path integral? I think C, B, anyway, CC bar, BB bar. This is the measure of path integral into the ghost. and we just introduce BB bar, CC bar. So this is the path integral we will consider, but we have to be careful about the boundary condition ferments. So here, B and C are Fermat field, so that the Fermat field, so that the usually if you go to the time circle, you have to impose the anti-periodic condition on Fermat. You have to introduce anti-periodic condition. But now, if you consider anti-periodic, it's a good exercise. The partition function vanishes. So therefore, you just introduce periodic boundary condition on the time circle. So that can be written in Hamilton formulation: B0, B0 bar, C0, C0 bar, Q to the L0 minus C over 24, Q bar, L0 minus C over 24 bar. So that's the and this minus 1 to the f really corresponds to periodic boundary condition. Okay. It becomes Euclidean. So this corresponds to the periodic boundary condition, and then this zero mode insertion corresponds to this. And we will compute this path integral, or you just sum over all Hilbert space. And Hilbert space is created by, again, you just apply all the creation mode. Let's look at the holomorphic part. C minus 1. Okay. Anyway, N1 and M1, B minus 2, and 2, C minus 2, and 2, and so on, to the vacuum state, which is the downspin state. Okay. Downspin state. And then, of course, N1 can be either 0 or 1. Okay. So it's fermionic, so you cannot have multiple copies. And we just want to sum over all Hilbert space by counting the weight, like here. So then it's now fermionic. So it's fermionic, so that the so for instance, so B minus 1 and 1 downspin will create the 1 minus Q. Oh, sorry, I think I should mention that again L0 of ghost is equal to minus sum over N B N C minus N, as far as I remember, minus 1. And as far as I remember, that's the case. Oh, I did again typo. Good. In the lecture note, but oh. Yeah, so in integer. Okay. So this is the zero mode. So therefore, L0 and B minus 1, B minus N is what? I think good exercise. B minus N times what? You should have similar thing over there. Similar to that one. What's the coefficient here? And the same thing here, C minus N, L0 is equal to, oh, sorry, I think this is bosonic, so it's just usual commutation relation, I think. Is it the case? Yeah, I think usual commutation relation. Usual commutation relation for bosonic and fermionic. Okay, so therefore, So sum over n is equal to n1 is equal to 0 or 1. It will give you this one. Can you see that? So this corresponds to just vacuum, and this corresponds to b minus 1. Okay. And similar thing, so v minus 2 and 2 with sum over n2 will give you 1 minus q squared. Okay. At the end of the day, so what we have is indeed trace. Oh, I have to be careful. There is some overall factor minus 1. Okay, so therefore there is an overall factor q to the minus 1. Q to the minus 1. Overall factor minus 1. And so therefore minus trace of minus 1. I just look at the homomorphic part. C0 q to the L naught minus c over 24 will give you q to the minus 1 minus c over 24, and then okay, that's well, how you get it. What's the central charge C for Gauss field? What is the central charge of Gauss field? Huh? 13, good. I mean, here it's just central charge of both, so therefore it's at 26. So C ghost and then, minus 26 plus Cx is equal to, has to be 0, right? And this is dimension is 26, and this has to be minus 26.
But why C is 1?
No, I just fix here. I just fix the mu equal to some particular number. I just only look at the dimension 1. And some mu is fixed here. So as I mentioned, I already erased. Seems like so there is no mu, right? So usually, if you consider all the dimensions, you have to include the mu here. But I just fix some particular mu. Mu is fixed. Only you look at the one dimension. So, and at the end of the day, I just take a product, because each dimension will give the same contribution. Okay. So therefore, what we have is B bar, C bar, BC is indeed equal to Q to the minus 1, C over 24, product of 1 minus Q to the N squared, and just square it. And this is indeed equal to 8 tau 3. Okay, any questions so far? So therefore, at the end of the day, what we get is L10 is equal to the volume of space-time and 2 pi Ls 26. That coming from this factor coming from a Gaussian integral of what was it earlier? This Gaussian integral over there. Sure. Gaussian integral, and then Gaussian integral, and then we have the integration over fundamental domain. Okay. So these now are 26, and then there's the 4. 26 times 2 minus 4 will give you 48. Okay, so that's, and this integration needs to be carried out the fundamental domain of the complex structure. And as you can easily see, if you do the Taylor expansion, so you get the q to the minus 1 plus 24 plus order q and dot 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 order q. So therefore q to the minus 1 corresponds to what? This term corresponds to what? How many first excitation states do you have? What's minus 1 means? Essentially what we did is L0 minus C over 24. So the exponent here is everything coming from the meaning of L0. Okay. Essentially L0 will give you counts so as I mentioned, L0 counts the level. So level minus 1 is what? Or level means the, anyway. So this one is tachyon. It's a vacuum. And this is the massless state. So this corresponds to mass. L0 corresponds to essentially mass. This is tachyon, that's why minus 1, and there's only one vacuum. And if you only look at the holomorphic part, there's a 24 massless states, as we already seen. And if you add if you add the anti-holomorphic contribution, you get 24 plus 24. 24 times 24. 24 times 24, and that is the massless states, the degrees of freedom for cross string. Okay. And then, so that's the correct string spectrum, bosonic string spectrum. And then furthermore, this eta function enjoys eta tau is invariant under SL2Z. And I think there's some factor here. Yeah, q to the minus. So this is T transformation and the S transformation. Sorry. What I'm doing is equal to so this is corresponds to T transformation and S transformation. It's almost same up to some factor. And this factor will cancel out the transformation rule of this measure. Okay. So you should check this transformation under SL2Z will cancel with this factor. Okay, So therefore, the partition function, so transpartition function invariant appears as V. And furthermore, so this fundamental domain so integration fundamental domain, so that avoid tau 2 is goes to 0. Okay? So tau 2 goes to 0 means that the torus becomes very, very small. Okay, the time direction is very small. Okay? And if you use the again power whatever the Heisenberg uncertainty principle, this naive argument, if time is very small, the energy will go to becomes high energy. Okay, so therefore we avoid high energy region for integration to compute the torus amplitude. So therefore it's free from UV divergence. So here you don't need to integrate over the high energy region so that there's no UV divergence for this integral. So therefore, you can just add one loop. The string theory is ultraviolet divergence free. Even though we know that the bosonic string have a graviton. Even here you have already graviton. Even if you include the graviton and compute one loop amplitude, that it's free from divergence, UV divergence at one loop. And that's what people excited. What makes people excited? Okay, any question? So that's the story of amplitude. Okay, I found lots of typo in the lecture notes still, even though I made a huge revision. Okay. Now we'll move on to superstring. Superstring. So far we have only the bosonic degrees of freedom but now we include Fermat. And then if you include Fermat, so the bosonic string is 26 the critical dimension, and now the superstring is only consistent only when d equal to 10. That's what you're going to see. And moreover, superstring, what's nice is no tachyon. And furthermore, so vacuum is stable. Okay. And then and moreover, one can see lots of things. So the superstring, if you study superstrings, there is five types of string. The 5 types of string theory. So the one is called type 2A and 2B. And you can quotient okay, and type 2A and type 2B, and also type 1. And it has to, this is the, lots of things. Well, type 1, heterotic, SO32, and also E8 cross E8. There's 5 types of string theory, so we will consider step by step. And then here you can have a D brane. Anyway, so maybe it's better not to mention. So both have a D brane. Type 1A, type B have a D brane. And then here, okay, so let's not talk about D brane. So let's not talk about D brane. Then here you have the unoriented. So this has SO32 Yami's degrees of freedom. And this is type 1 is the unoriented. So this is, if there's no D brane, it's a closed string. This is the unoriented. Both open and closed. Okay. And it can have the Yami's degrees of freedom SO32. This is the only gauge group you can have without any brane. So this is the heterotic. You don't have the brane, but you can have the Yami's degrees of freedom SO32 and the E8 equals E8. That's the consistent gauge group for Yami's degrees of freedom. Okay. So we will see step by step how we show up. Type 2A, type 2B, type 1 heterotic. And they are all related by duality. So they are all related by duality or orientable projection. Orientable projection. That's what we are going to see. Okay. Okay, so there are 2 major formulations superstring. One is the worship viewpoint, and another is space-time viewpoint. So superstring is a supersymmetry. Is a symmetry. So as we will see, symmetry between boson and Fermat. And then this supersymmetry can be seen in both aspects of worldsheet or space-time. And worldsheet formulation is called Ramond-Nebieu-Schwartz formulation. And this space-time formulation is Green-Schwartz formulation, and we will pick this perspective. We will pick this perspective. So RN's formulation is you start with action. I call it as matter. 1/4 pi. Usual thing is curve Z. So now we just look at the space-time is just a plot. And now you include Fermat. And the mu runs full. So let's first do the or maybe if it is Minkowski 0, 1, total runs full. If it is Minkowski, let's first consider Minkowski signature. Okay, so then so you just have bosonic degrees of freedom, but now even though space-time has the Fermat degrees of freedom. So this is the Fermat degrees of freedom. And now you can check that it's invariant under the following transformation. And anti-homomorphic, you just took a bar on it. I'm not gonna write it down. And then anti-homomorphic. So this action is invariant of this transformation. This is called Walsh supersymmetry transformation. SUSY transformation. So somehow, once you add the boson and fermion, immediately some symmetry show up, such as which is called supersymmetry. And this supersymmetry transform the bosonic field to fermionic field, and the fermionic field to bosonic field. This is a typical nature of the supersymmetry. So therefore, epsilon is treated as a fermionic variable. And then, since there is symmetry, so the Tensor theorem will tell us there is current. So there must be supercurrent. Tensor theorem is supercurrent. Okay. And the supercurrent just as follows. Supercurrent is Tf of Z. And anti-homomorphic. I just write down the homomorphic part. Okay. So this is called supercurrent, and the anti-homomorphic part too. And then one can just consider and the stress energy tensor. Stress energy tensor can be written as dB of Z. As the usual piece we have before, and also Fermat piece. You have now Fermat piece. Okay, now so remember. Oh, sorry. No bar. Sorry. Yep. No bar here. So, of course, you have the homomorphic part of the stress energy tensor, but I'm not going to write down. So, the same thing happened here. Okay. So, and then, so you can just take the TTLPE, and then, so we as before we have the OPE between bosonic field is indeed eta mu nu up to some factor for alpha prime over 2, and then log Z. And this one you did in the homework, so other homework part I'm not going to write down. So you did homework to derive this this OPE, and then so if you use this one can just show that the is indeed you can just have the whole Z square, so these reports and the usual piece. So that's the TTOP. So now remember that the here it's a bit different from before due to the presence of the Fermat field. Okay, and also you can have the OP between the supercurrent and the Fermat current. And this one you get 3Tf over 2 T squared plus so this means that the supercurrent Tf is primary of what is the dimension? What dimension? What is the compound dimension of supercurrent? What are the dimension of supercurrent? Compound dimension. Yeah. It's compound dimension 3 over 2. That is very natural in the viewpoint that so you already knew that the psi has primary of compound dimension what? Psi mu. Mu is fixed. 1 over 2. Okay. So if you look at here, this has conjugation 1 over 2, and this has conjugation 1. So if you add them up, you get the 3 over 2. Okay. That's very natural. Yeah. So central charge of this matter field is 3 over dO. So it's different from before because of Fermat contribution. So as I mentioned, this psi field has the central charge 1/2. Central charge of each fermion is 1/2. Central charge of each boson is 1. Okay. So each dimension will give you 3 over 2. Okay. And if you have total dimension, if you add all the dimension, you get the 3 over 2 times d. That's how you get this number. Okay, to end this. So one thing you have to be a bit careful about the boundary condition for ferments. Ferment, you have so you have a wall sheet. The cylinder is closed string, and the ferment can have the following boundary condition: psi T sigma plus 2 pi is equal to plus psi T sigma, or it's called spin structure. Sigma. Okay. Plus minus. So once you go around on a spatial direction, by 2 pi, I already forgot which direction I took this direction. Yeah, I think this is the direction. 2 pi, you can impose either plus or minus. That's called spin structure. If you have a non-trivial fundamental group, you have to always impose for Riemann surface, spin structure. Then this one is called Ramond boundary condition, and this is Navier-Schwartz. Okay. So this is anti-periodic. And then, so again, so you can just have the transformation of the plane but this is W is equal to sigma plus IT, and e to the minus IW is equal to Z. You get a Z plane. That's from transformation. And then since the psi has a transformational role, its primary or conformation 1/2. So W, so therefore this is indeed equal to e to the minus I W over 2 psi mu W. So therefore, if you do the 2 pi rotation plug into here, the sign will flip in this plane coordinate because of, just put the 2 pi here, you get the just minus I pi. So therefore, you have to flip. This means that the this is Ramond, and then Schwartz. So you have to be careful which coordinate you use. So for cylindrical, plus minus, are periodic, anti-periodic. But for plane coordinate, you have anti-periodic, periodic. You have to be careful. Okay, so of course we will use this coordinate for time being. Then, so due to the ambiguity of or the two choice of boundary condition, you have to be careful about the mode expansion of Fermat. So if you have psi of Z, which is the mode expansion usually PP. So when u takes 0 or 1/2, either Ramond or negative Schwartz. So as you can see, so if it is 0, so once you go around, a 2 pi rotation will give you minus sign. Whereas if you put this due to half integer mode, and if you put the integer mode, you get the plus sign once you rotate. So that's the difference between bosonic and boson Fermat. So, and then the canonical quantization, we can do the canonical quantization. I mean, it's almost same as the before. Just repeat in the quantum field theory. You just we also have similar computation ratio BC cost. And now we can also expand. So now, first we want to see what is the vacuum energy. So first, and in bosonic strings, what we did is indeed you just introduce the Lm, which is something like a sum over alpha n minus n. Yeah, and you just look at what is the computation relation between 0 mode, yeah, and then alpha minus n, alpha n, and 0 mode. But from here, so from this computation relation, you get 1/24 from each dimension. Minus 24. We will do the same thing. And then that and times d minus 2 will give you the tachyon energy, tachyon mass. So that we will do the same thing for including this fermatic degrees of freedom. Okay, let's move on for a while. So again, so T bosonic energy moment. And we have again a similar model expansion. Here again, you have the Ramond and maybe Schwartz will appear because again, did I erase? Oh yeah, sure. The Fermat current has the fermions, so that has the that depends on the boundary condition we impose. And then, so it's straightforward exercise to compute model expansion in terms of alpha and psi. Over there, that's, I mean, from expression, you can just have model expansion. But ambiguity again show up for zero mode. No ambiguity, some subtlety show up. Sorry. So this part you can easily show. You can easily show from this part, but again, so if you look at the zero mode, you have to be careful about normalization, normal order. So that the so you have some constant delta M0. Another thing is this is the supersymmetry. It's called supercharges. Yeah, I mean this model expansion here is called. This is supercurrent. This G is model expansion. Especially G0 is called supercharges. We give you some over alpha n psi r over n. N is here alpha and psi commute, so it doesn't matter normal order. Normal order. Okay, and then so the exercise from here, from this TT or PE, one can obtain the computational relation between L and G. L is the Biot generator, G is the super generator. That's called, indeed, it's called n equal to 1. N equal to 1 supersymmetry. Supersymmetry in two-dimensional language. That's called n equal to 1 in left moving sector. So since you have right moving sector, holomorphic sector and anti-holomorphic sector, so at the end of the day, you get the n equal to 1,1 supersymmetry algebra. From this analysis, RNS formalism. That's going to be homework. I didn't post a homework yet, but that is going to be homework. Okay, so let's look at let's try to determine n and let's take a rest. So again, so from normal ordering, so let's look at the L0, and you just look at the normal ordering of, and the cost of normal ordering. And again, here, if you just look at here, plus 1/2, okay, so this is the, oh, am I wrong or not? Yeah, I think I'm correct. Yeah, and then plus m plus delta m0. Okay, so this is the case, and then so you just look at the again bosonic contribution. Again, you do the same thing. Sum of n goes to 0. Yeah, is indeed 1 over 24, right? So did you remember? Did you minus 1 over 24.
1 over 12.
Huh?
1 over 12.
Thank you. 1 over 12. So that how you obtain is, as far as I remember, n e to the minus n epsilon times n, and this is indeed derivative with respect to 1 over e to the minus epsilon, right? That's what we did, right? How we did. And minus, I think, as far as I remember. Yeah, minus. And this is 1 over epsilon minus 1 over 12, and so on. And I ignore this one, okay? And you get this one. And another thing we need to take into account is here. So it depends on, okay, I think I should go here. It depends on, so here, sum over R, if it is Ramond, if you're Ramond, it's just the R is the, am I correct? I'm just worried about what I'm talking about here. Yeah, I think okay. Yeah, so Ramond, the nu is equal to 0, so that the R is C, so this will give you minus 12. On the other hand, you have for Nebish, this is Ramond. Nebish-Schwarz, you have half integer. Okay, half integer. And this can be also easily treated the same way. So you just do the same thing. So you just do the following. R e to the minus R epsilon, sum over R, so the 1/2. E to the 1/2. Am I doing correct? Just correct me if I'm wrong. Yeah, 1 minus e to the minus epsilon. So that's what you're going to do. So this the difference only appear here, and it's sorry. I think I should put epsilon here. Yeah. So this is correct thing. So this will give you 1 over epsilon, and it turns out that 1 over 24. You can just do the simple computation and minus as far as remember plus. Oh, I forgot. Just a moment, I have to be careful. Good. So this should be plus. Okay, so therefore, at the end of the day, so including shift of the cosmic energy, so AM. So the shift of cosmic energy appear here is C over 24. And then, but for bosonic and fermionic, so this is Ramond. Let's look at Ramond. So this is coming from bosonic states. Bosonic 1/2 times minus 1 over 12, and then here 1/2 times minus 1 over 24. And I don't understand why I have the plus sign. Just a moment. Why do I have minus sign here? Sorry, is it minus sign? Sorry, I got confused. So it should be minus, right? Is it the case? Oh, this is okay. This is okay. But once you take the normal ordering, you get the minus sign. So therefore you get the minus 1/2. Minus 1/2 plus this one, you get a plus sign. This is okay. Sorry, thank you. And then, so we know Cm is this guy, Cm is this guy, and if you sum them up, this is Canonical, and you just plug that one into here, you get the 1/16. Okay, and then M is equal to Cm over 24 plus minus 1/24. This is bosonic states. However, you have fermionic states, D. So you 1/24 times minus 1/2 will give you minus 1/48, and this is equal to 0. And then we short. Okay, so this is the computation, the cost of normal ordering that appear in the zero mode of the solution. Let's take a break. So if you have done homework, just submit. I forgot to bring sweet today. Sorry. I'm too busy. Yes. No.
The first one I want to ask here, there is zero mode. Why here we do not need zero mode?
So here, just integration over the torus will give you just zero mode.
Like this one.
Yeah.
And for the tree level, amplitude, why there is not appear the such term when calculate such one and such one, these things only appear this form makes sense.
Because we only look at the zero mode. That's actually a good question. That's actually a good question. Let me think. So we just only focus on zero mode of Gauss sector. So therefore, okay, I see. So transformation function, you have the whatever C. Indeed, ghost, and a bunch of insertion. And then, but divided by usually CC1 e minus C ghost. And this one, the insertion of this. I mean, it's a good question. In fact, if you don't, zero mode itself take care of themselves. What I meant is that the. Oh my goodness! I think I should go to the office to catch. So zero mode is essentially this is zero, right?
Yeah.
So this is the zero mode. So therefore, action is indeed equal to zero. Do you remember? So the dz square b delta c. This is action, right?
Yeah.
So therefore, zero mode for action is indeed zero. So e to the minus s ghost is indeed 1.
And similar for the field x.
For field x.
For matter sector.
For matter, you include so e to the ikx and a bunch of things, right?
Yeah.
This one just can be computed by just taking the OP.
Taking OP already.
Yeah, take care of all the action. Yeah, it's.
And also when you take the OP for example for 3 terms.
X3, okay.
And it seems you need to take the contraction
Yeah.
and the contraction and
It's a good exercise to do. So I think the first you need to do. So then X1, will give you normal order. Times X1, 2. And I think and next you just contract this one
but this should has 2
it only have a corner. C1 and C2, right? Now it becomes C2.
yeah. And the contrast from this one and this one is need to plus this one plus this one, or since there seems no sum.
No sum.
Yeah, just
what I meant is E I K X I K X I K X. And first contract this one, and then you get the sum factor times normal ordering e to I K, another copy of I K X. And then you just take the OP of this one. Then you get another copy of Z. That's how.
And this star function comes from the when do the OP and then the
This one. Yeah. And then if you take all the expectation, it should be delta function. It should that give you delta function.
and also this 0, what does that mean?
So no puncture. So Gn equal to 0. So you have a question?
I understand how this one compute. This you say compute over the torus.
Yeah.
Why do you get the
So I told them about I have two times, right? This was computed. It's just will give you just integral over torus will give you. Torus will give you only zero mode.
How do you integrate torus?
What do you mean?
Precisely how this.
Because e to the I theta d theta is equal to what? 0 to 2 pi.
This is 2 by I.
Huh? This one is give you what?
This I is 2 by I.
Why?
Or 2 pi.
Why? It's just Fourier analysis. Why is it 2 pi? Just integrate over this one. What you get? Why? You cannot do this integral? Please do integral of this one. You cannot perform this integral? What? What's the answer? Are you okay? Zero, right? So all the term proportional to e to the I theta is zero. So only constant mode is contributes.
就是它那个 patch，两块对两块之外，全值和非全值对应的是最多为这一方的一个公式，所以没有上多是物质吧。
Okay, let's continue. So, so now, again, we will introduce Gauss field, and again, so where were we? So we determined this one, right? This one. We determined this one. So then we will introduce Gauss field. So we will introduce Gauss field from now. Is 1/2 pi e squared c, and now we have the Fermat ghost, but again it's a supersymmetric, so you have to have bosonic ghost. You need to introduce. So even Gauss sector has a supersymmetry. So I'm not going to write down supersymmetric transformation, but it's easy to find. It's a good exercise, you guys, to find a supersymmetry. And now, and the similar analysis as before it will tell you that the okay. And then you can compute the
why there's the minus sign? I think this bosonic, so there's no minus sign. Why?
Am I doing very stupid? Am I too stupid? Right? What are you talking about? Okay, so again, so the So you can check that this is again, you can do the same computation as before. So indeed, so you can do the same computation to compute the stress energy tensor, or to this OP to be consistent, you should have the component dimension gamma and beta, the primary of component dimension 3/2 as far as I remember. Yeah, this is minus 1/2 of 3/2. So that's so therefore that appears 3/2 appear here, and then if you take and so that you can just check TB. Z and beta 0 is indeed equal to 3/2. Oh my goodness, I'm already running out of my energy over z square plus like this way. You can just check. Is minus 1/2 gamma. So then again, so you can have the supercurrent. So this has supersymmetry. Supercurrent is a good exercise. Actually, it's included homework, so you should do that. So it's supersymmetry boson and fermion. So you have supercurrent plus 3/2 beta pressure C minus 2p. Okay, so that's what you get. So for instance, yeah. So you can compute. So you can compute TTLP, TT ghost. Sorry, I think I should use ghost. And ghost. And TTLPE of ghost. This is again a tedious exercise you can do. But you almost compute it on homework. You compute a homework. So you know that the TTLP, this bosonic. What was it? So this fermionic part will give you minus 26, and this one will give you 11. So that the indeed central charge is indeed minus 26 plus 11 over 2, 1 over z square 0 and z plus force. Square plus t ghost. You just stop. You already knew. Okay, so that the c ghost indeed is equal to minus 26 plus 11, which is minus 15. So therefore, total central charge is 3/2d minus 15. And this becomes 0, okay, while anomaly free when D is equal to 10. Okay. So now you have a critical dimension. So thanks to the Gauss field, Fermat field, and thanks to Fermat field, you have additional Gauss of plus 11 and 3/2. That will make the critical dimension will 10. Okay, so now we get the critical dimension. And then now let's compute the cosmic energy, including this Gauss contribution. Okay. So now we have model expansion. Again, so here the Gauss field has the opposite, how to say, partition transformation, so that now the bosonic field has some, how to say, the depends on boundary condition. So now we have BR plus 3/2. Now this bosonic field has the choice of boundary condition. So the Gauss has the different the partition transformation. You have to do the partition transformation. Gamma R Z R minus 1/2 R minus 2Z plus Z. Okay, so again, nu. So nu is 0, 1/2 is Ramond and Mobius-Schwarz. Yeah. So and then we impose the condition beta R and the gamma S is equal to delta R plus S. Okay, so then again, so we just write down L0, Lm. So the stress energy density takes a form, and you can just take the following form: sum over n plus n. Okay. So you have ambiguity in zero mode. Actually, I have now a question to the answer to the question to you. Indeed, why do you get the -1 here? So, okay, let me finish writing everything. Then I'll answer the question. So, GR ghost is equal to sum of n C Okay, so this is the supercharge, and this is Bielsel mode. And his question last week is as follows. I briefly answered the question to him via WeChat. His question is as follows. So before going to the supersymmetry, the ghost action. So let's leave it as it is. So ghost action. Yeah, again, I don't like this joke. So the ghost, as ghost, is just the action is 1 over 2 pi, and d squared z, b partial c. And then if you look at the zero mode L no is indeed equal to b minus n c n minus n, as far as I remember, n is the integer, and minus 1. I think that's the. So this one corresponds to a ghost for bosonic string. So this is a permanent mode, but it's a bosonic string. The question is how to get minus 1. So as I mentioned, this A constant is C over 24 plus a normal order ambiguity. And the normal order ambiguity is indeed coming from so this n, so that the sum of n is equal to minus n greater than 0 is it needs plus 1 minus 1 over 12, and since this is fermionic, the opposite sign, so you have 1 over 12 plus opposite sign, and C is equal to minus 26 over 24 plus 1 over 12, you get minus 1. That's another way to get to this minus 1. So yeah, I think I should write it in the lecture note too. So, and we will do the same thing for including the experiments. So just this is bosonic strings, not fermat, but the ghost field for superstring. Sorry. So a ghost is indeed minus 15 over 12. 24 minus 15 really come from ghost central charge, or maybe I just see ghost, whichever. C ghost plus 112 coming from here, and 112 coming from here. So again, here, if you look at zero mode, what you get is the R, sum of R. R is C plus nu beta minus R down R. Okay. So the gamma R, and then we just pick this R up to sign. That will give you again, if nu is 0, you get the minus 12, and then you get here. And for Navier-Schwarz, you have C ghost 24 plus the same piece 12, but now we have the half integer for Navier-Schwarz. To be honest, I don't understand why this is a minus here. Sorry, I just got confused. should be plus, right? Yeah, there's a typo, sorry. It's typo, sorry. Oh, I'm relieved. This is typo. Is equal to minus 1/2. So let's do a computation. This is minus 15. I'm glad it's typo. Minus 15. And this will give you 3/24, right? And if you sum about minus 12, you get minus 1. Good. It's typo. So there's a typo in minus sign here. Good. So then, okay. So then let's put compute total is a matter plus a ghost, which is it used to be what was it? So 1/16 d plus that one minus 8 when d is equal to 10, this is 0. Come on. And another thing we have zero. It used to be a total of 0, but however you have a minus 1/2 contribution. Okay. For Navier-Schwarz. So this will give you the cosmic energy, so that happily when d equals 0, d equals 10, sorry, d equals 10, Raman sector. So this contribution is indeed so a total 0, so there are no tachyon. No tachyon. It used to be a total. A total is indeed equal to, I was it used to be 24 minus minus 1. A total is minus 1. But so that will give you tachyon. That will give you tachyon. But now there's no tachyon. However, you have to be careful on Navier-Schwarz. A total is minus 1/2. Looks like a tachyon. There is tachyon. And as we will see, this tachyon model will project it out. By so-called Dsl projection. So that's what we are going to see. Okay. So we are going to learn what the Dsl projection is. So before that, let's look at some Fermat spectrum. Okay, so I'm already running energy. So the psi has a mode expansion d plus nu psi r to r plus 1/2. Okay, psi of z. Okay. So now we will consider some vacuum. So in Navier-Schwarz, ground state is the, you can just consider, so Navier-Schwarz, nu is equal to 1/2, so therefore you have psi 1/2, R, the positive mode acts on vacuum in Navier-Schwarz vacuum is equal to 0. So this is the annihilation operator. You can ambiguously define the annihilation operator. However, for Raman, you have a 0 mode, so you have to be careful. Okay. And we impose that the so we impose the condition that the so we consider this Navier-Schwarz vacuum is indeed sorry, what I'm writing, sorry. So fermionic. So indeed this Navier-Schwarz vacuum is fermionic. This is, you can consider as the as a definition, let's move on. So then you can consider Raman. So you now have a 0 mode. Okay, 0 mode satisfies so-called crippled algebra. So from here, let's go crippled algebra. Okay. So you have to be careful. So how it the vacuum of this there is no unique vacuum. So it should be representation. So 0 mode. Yeah, so therefore there is no unique vacuum, so it will give you the ground state of Raman becomes so-called spin representation of SO or spinor group of 1, D minus 1. Do you know spin group? Or D is equal to 10. We are going to consider D equal to 10. Do you know spin group? Spinor representation. I mean, do you know fundamental group of SOM? Fundamental group of SOM. Have SO3.
Spin group divided by dt.
Good. So what is the fundamental group of SOM? What is the fundamental SO3? C2, good. So you just rotate 2 pi. You won't get original position. But if you further rotate 1 more 2 pi, you get the original position. So SO3 is double covering of SU2. So this is called spin, indeed spin 3. Good. He knows. So SO3 have the fundamental group Z2, so you can have universal covering. Universal covering is called spin group. So this is really rotation inside SO3, 2 pi rotation SO3, and another 2 pi rotation SO3 will give you one 2 pi rotation in spin group. So that's the so anyway, so you can have a spinor representation for SO3, even SON is okay. Another way, do you know this one? I can just show you. So there's a belt. So you have rotate, let's say 2 pi, and just bring it down, and then here you won't get any. You cannot undo the rotation. But if you do 4 pi rotation, 1, 2, 3, and 4, and then bring up and going down, and you get the original. So that's the rotation inside a spin 3 group, whereas this original rotation, 2 pi rotation, just you cannot undo the rotation. This is a rotation inside SO3. So that's really give you the rotation inside. I wouldn't say rotation, or this will show the fundamental, non-trivial fundamental group of SON, SO3. Do you know who first showed this trick? Yeah. Good. So that's how Dirac explained the spinor group. So that's called Dirac's belt trick. Yeah. So anyway, so that's the spin group, how spin group, how the Dirac explained. So we will consider this spin representation. So now I'm not going to explain everything, but I just created some Fock space in spin language. That's what we want to consider. I is equal to 1. Okay. So you define this gamma, then this gamma will satisfy the following. And then gamma plus ij. So the rest are the trivial. And the gamma plus minus will act as the creation annihilation operator. Not creation, rating and lowering operator, and that generated 2 to 5 spin state. So you have like a S0, S1, S3. So I. Oh yeah. So I runs for. So here each S spin up and down. Okay, spin up and down. And then, so gamma plus minus plus axon down, we'll get plus minus acts on the up, how to say, up arrow, you get the down spin. That's how it acts. This gamma. That's called spin representation. So that would create indeed 2 to the 5 state, which is 32 states. Okay. Okay, so and then one can define chirality operator. So chirality operator is as follows. So the gamma 11 is I just define some factor 2 to 5, psi 0, 0, psi 1, psi 0, 1, dot, psi 9, 0. Okay. So given a Crefeld algebra, one can always define a chirality operator, and the chirality operator acts as some acts as this state. So let's call this SK as the plus or minus its eigenvalue under this spin representation. It just how to say acts as plus minus 1 on this spin representation, where if plus you get the even number of bottom spin and the odd number of bottom spin. Okay, so that's how you get. I mean, this one is familiar. So in QED, you have a. So this gamma is zero mode, indeed the same as gamma matrix you saw in the QED. In QED, Lagrangian can be written f mu plus psi bar e slash minus m, maybe I here, psi. This is Lagrangian. And this slash is indeed gamma mu, pressure mu, depends on E and mu, and maybe I here, I already forgot. It depends on the notation. And this gamma matrix, the same as this psi 0, 0 mode. So in gamma matrix, you already familiar. This is a Crefeld algebra you impose in Peskin-Schroeder when you learn it. And then gamma 5 you define as some number, I think some number times gamma 0, gamma 1, gamma 2, gamma 3, right? And this gamma 5 corresponds to gamma 11, this chirality operator. And this gamma 5 will give you the chirality, right? Psi minus. Or Dirac spinner will decompose wild spinner. And the right moving spinner or left moving. How to say? Chirality, right chirality and left chirality. That's decomposition psi plus or minus. That's exactly what I did here. So, okay. So this 32, people write a bold letter 32. 32 is a spin representation of SO 1,9. Okay, 1,9 is decomposed into chirality representation. Depending on plus minus of under this gamma 11, plus minus decomposed into irreducible representation. Okay, so that's the crash course of spin representation. And now we are going to introduce the Dsl projection. Okay. So let's talk about Dsl projection from now. So first, for physical state, to determine physical state, we again need to do the BRC quantization. In addition to the, for this fermatics theory, you need a so-called Dsl projection. So let's review what was the BRC quantization. So BRC quantization is indeed determine physical state. So BRC charge is indeed, I cannot write down BRC charge. So essentially, BRC charge is the as follows. Oh my goodness, I should have. Essentially this one, C TB plus CTB plus gamma TF plus something. Let me cheat a little bit. That's why I bring Poczynski. Oh, it's meaningless because I wrote volume 1, sorry. For the superstring, you need volume 2. Oh my goodness. Anyway, laptop is there, but anyway, so plus something. So you should check the Poczynski. So Poczynski 10.5 point something. The reason why you get this is the BRC current. Indeed, BRC current is like this one. Oh, I already written down. Sorry, I have written down in lecture note. Sorry. Plus one half C T ghost E plus gamma T ghost F. This is matter and matter. So the reason why you get you will get is always, this is a generic feature of BRC. BRC is QB, and if you take commutator, you get that ln. And then QB, this is generic feature of BRC. So if you take the BRC translations of this ghost field, you always get the stress and the BRC generator. This is generic feature. The same thing here. If you take commutator between BRC charge and the beta ghost, you get the supercharge. And this is generic feature. So therefore, essentially, the rough form of the BRC current is C times the stress energy tensor. If you take OP with C and B, you get the 1 over Z. And if you integrate over the, if you do the contour integral, you get the generator of the generator of the stress energy tensor, energy momentum tensor. That's why you get the L. So essentially, what you get, I mean, if you do the homework, you already knew that. The same thing happens. So to get the OP between OP between J and beta, essentially the contraction gamma and beta essentially will give you supercurrent after factor. And that's why you get the supercharges here. That's generic feature. And then so then we again introduce the fact that the ln positive mod and gamma is equal to 0 for physical state, then L okay, sorry. Again, so physical state is so QB has to be annihilate. So physical state is again you need to impose HQ closed, QB closed, closed divided by H QB exact. Okay. So this will give you the condition that the state, physical state. So this commutation relation implies that the state acts on this one is unphysical from here. And then let's see, state is UR of M some state are unphysical. Because they can be written in terms of Q exact form. So you can just project out this kind of state. And furthermore, you need to impose so-called Dsl projection to Dsl projection. The purpose of Dsl projection, unfortunately, I don't have any. So to have equal number of bosonic and fermatic state at each mass level. Unfortunately, I don't think I can get to the end. So this is the purpose of Dsl projection. So supersymmetry, you want to have number of boson fermion states as the same. So to do that, we need to have some this for NS sector. So you just introduce some operators so called GSO, which is 1 plus minus 1 to the F over 2 in NS sector, and that will project out. If this is the so you have to apply all the state that is created by 0 and K. So that, as I mentioned, this is vacuum, and many state, how to say, you can just act on the, how to say, alpha, again, minus, what was that? Yeah, anyway, so all the state minus 1 to the n1, again, the same thing. Bosonic states and also fermionic states can act on, fermionic creation operator acts on R minus, okay, minus 1/2, minus 3/2, and so on, can act on. That create the Fock space of this maybe short sector, but you first you have to impose this projection. So therefore, for instance, if you act a Dsl projection, acts on, for instance, vacuum, as I mentioned, this has fermionic vacuum, so the 1 minus 1 over 2 is 0. Equals 0. Okay. So therefore, the Dsl projection GSO projects out the NS vacuum, and next sector is the 0K and some field axon, fermionic field axon. So this is the you can consider this one is the ground state of the maybe shell sector. Okay, unfortunately the ring the bell rang, so I have to stop here. So next lecture I will explain GSO projection a bit more detail and talk about Transpartition Function for superstring. Okay, let's stop here. So yeah, so therefore there's no tachyon, even Navier-Schwarz. GSO help us to do that. Okay, let's stop here.
就算没有什么词汇上，我不能直接把它看见非常高，有什么区别？定义式里不就可